share my screen. Can everyone see that?
Yep.
Okay. I can't see anybody, so say anything if waving hands frantically won't catch my attention. Well, I want to thank everyone for allowing me to present tonight and share my thoughts on microcontrollers and the big data landscape. And to get started, let me share a little bit about myself. My name is Nick Hepperman. I'm an electrical and computer engineer, and I have a passion for writing software. So I find the marriage of electronics and software creates some, the marriage of electronics and software creates some pretty awesome possibilities, and it fills a vital role in many critical use cases. To give you some idea of my background, I started my career as a software engineer where I was integrating electronic imagery and video systems for defense applications. Then I joined an e-commerce company based in St. Louis with a partwise focus on imagery and video processing and also on enterprise software in general. And for the most recent past few years, I've shifted focus to data processing and machine learning technologies in an e-commerce setting. So on tonight's discussion agenda, first we'll go over microcontrollers in general. What are they? Why are they important? Where can you use them and where will you expect to encounter them? Then we'll go over a public rollout of my open source software project, the Embedded Device Prototyping Framework. That happens tonight. Also, we'll compare and contrast programming on microcontroller platforms versus other programming platforms like computer workstations. And lastly, I'll share with you some embedded device prototyping kickoff tips and some closing thoughts. So before we dive in, let's talk about whether this will be a presentation or a discussion. I much more enjoy discussions over presentations, so I want you all to be encouraged to shout out anything, jump in and ask questions, probe my shallow knowledge and pitch in when you think you can. And so with that said, let me open the floor. Who here has already done some electronics work or thinks they'll do some in the future?
Hey, this is Jacques Wilson. Okay, I realize after hearing you guys talk, I'm a complete, absolute hobby novice, but I play with Raspberry Pi, Picos, ESP32s. So when I saw this setup, I'm like, hey, I'll jump in with that. So I might be behind on the software talk, but so I'm interested in that regard.
I think this is like geared directly at that. So no, this is for you, I think.
Awesome. Well, and actually the one piece where I'm interested in the big data concept is machine language and like something like OpenCV and kind of marrying those two together. So anyway, TensorFlow, all that kind of stuff. So yeah, I'm definitely interested. And yeah, thanks.
Sure. Anyone else? Okay. All right. So now we'll go into microcontrollers and what are they? So microcontrollers are small computers that come in the form factor of a single chip. Inside them, you'll find the main components of normal workstation computers. You'll find non-volatile storage to hold the code that executes, settings that get remembered between power cycles, sometimes readings from peripheral devices. You'll have memory that'll hold the software instructions and volatile working storage. You'll have I/O components such as individual pins for outputting voltages or reading voltages. You'll have data buses for communication between additional chip packages and UI elements and a processor to control the execution of the firmware. So microcontrollers have a few superpowers that help them fulfill some very important needs in our data landscape. First off, they can be very cheap. Even in the pandemic times with chip shortage prices, a person can buy 3 microcontrollers with all the connectivity hardware in single package boards for under $20. Microcontrollers are also small. So you can see in this picture, the microcontroller is not much larger than the tip of the ink pen. So often microcontrollers come mounted to boards that provide essential connectivity between the microcontroller and other components. And as you can see, even the size of the microprocessor and the connectivity components, the form factor still allows them to be used in many applications.
So are you saying just that one chip on the picture with the pen tip on it is the microcontroller? Everything
so,
else is just like extra?
yeah, I mean, a lot of it is necessary. So like this is the USB connector, and sometimes there'll be a special USB I/O chip that goes with that. Here's the reset button, and here's some pins that you can like toggle on with jumpers to set up different configurations of the device. But just that device by itself is like the heart of everything that's there. Sometimes there'll be some extra resistors, but yeah, that's it for something that you can code and operate against and provide I/O.
Wow, nice.
And then this is my favorite one. Microcontrollers are bridges to like the real world. So in data capture type applications, the microcontroller will interact with the sensor and like capture voltage readings. And then the microcontroller can also be used to command larger systems. So it can be a component that say provides the command and control to larger physical machines. And it can bridge electromechanical human interfaces, so push buttons, LED screens, joysticks, and so on. So it really provides a lot of interaction with devices. So where will you encounter microcontrollers? I think the better question is, where won't you encounter microcontrollers? With the benefits I mentioned earlier, so they're used pervasively in many types of applications like healthcare-related devices, toys, automotive components, controllers, household appliances, and on and on. So how are they involved in big data? In the Internet of Things, there are numerous scenarios where microcontrollers come into place. Let's take this one example scenario where a temperature sensor exists in an agricultural setting. The microcontroller captures the readings from the sensor, transmits the readings to the cloud, and finally the readings are persisted to a data store. So that concludes the first part where we talk about the what, the why, and the where of microcontrollers. I want to take a brief pause. Or does anyone have any questions so far? I would also add that's like not the only places you'll find microcontrollers, but that's like especially in the hobbyist space that like Jacques is talking about. Interacting with sensors and controlling small devices is where a lot of that happens, and a lot where the software I'm going to show off here in a bit is going to come into play. So now let's tie microcontrollers and embedded systems and innovation. So at high level, we talked on how the microcontrollers fit in the digital landscape. The attributes of the microcontrollers make it a core component for many types of applications. Their small size, they can fit in almost any sort of form factor product and facilitate many use cases. And the microcontroller has been a key component of many products and will continue to be a key component of many products to come. Now, let's focus on my exposure to microcontrollers and how it led to the open source project we're discussing tonight. In my first 7 years out of school, I worked daily as a software engineer integrating microcontrollers with computers. And then I shifted focus to apply software engineering to the e-commerce space. A while later, I found myself dabbling back in electronics again in my free time and doing a few personal projects. After the additional years of software engineering and exposure to some really great-minded engineers, habits, and concepts, I realized how much boilerplate code could be generated by the code needed to simply pass data back and forth between embedded devices and workstations. And with my additional learnings and experience, I realized I could use better software design. I could code less of my projects and prototype my work much faster. And thus led to the open source project, the Embedded Device Prototyping Framework, or EDPF for short. And there's two big takeaways I want everyone to leave with about the EDPF. The number one takeaway, the EDPF is to embedded devices as Swagger is to APIs. Who here is familiar with Swagger? Would you mind explaining like what Swagger does?
Sure. Yeah, Swagger is the specification, the contract that your API is going to adhere to, and then they provide you all the tools around the spec. So like linting and client generation and even a little like server skeleton generation, things like that.
Yeah, yeah, and the part that I really think the EDPF is like Swagger, and especially the UI component for exploring UIs. So Swagger has this really convenient user interface, which allows developers, to learn a lot about the API with a minimal amount of effort. So likewise, the EDPF provides UI in the host application that inspects the microcontroller's firmware. The firmware responds with its capabilities, and the host UI configures itself for easy interaction with the device. The number 2 takeaway is that the EDPF provides additional UI and host machine software tooling to ease in development. So this tooling includes charting, console interface, command interface, which acts a lot like functions in programming, connections tool, macro tool to repeat sequences of device interactions, and logging. And so now I'll give a quick demo. Can you guys see that? A application just started up. Okay. All right. We'll close the splash screen here. So as you can see, before any devices are connected, the UI is pretty much disabled. I'm going to use the connections tool to establish the connection. And once that happens, the host app queries the firmware for supported functionality, and the firmware responds with its command descriptions. So that's what this is here. For each command description, a UI component is created. And if the command accepts arguments, the UI provides named field input boxes that are strongly typed. So you can see in this command, the command is named param.io, and it has these fields, which they're named with the type just to really stress that point home. And then the host UI allows you to interact with those different commands really easily just by calling an execute. So if I click execute here, I'm asking the device to tell me information about it. If I want to feed it information, such as I want to feed it values, I can enter in some numbers here. Do 45 there. This is an int 8. I don't know if you guys can see this or not, but there's different inputs in here. I'll add in a double, 1.23. And I'll add in a bool value and hit execute. And so after I've hit execute, the host UI sends that information to the board. It kicks off the command, and then written in the firmware of the command, it reads those values back and just echoes them. And so clicking the execute, you can see the flow of the I/O in the console window.
Can I ask a question here before we go?
Absolutely, please jump in.
So you're saying that you use a COM port or just a USB or?
Yes, so it is a COM port, which is the USB connection. If you had a real physical COM port, that would work too. But is this Jock? Sorry, I can't see who's talking.
Chuck, sorry.
It's with a lot of the devices today, especially the like hobbyist are the ones where you're not in like really high throughput industrial settings. Like all of them connect with USB, and it appears as a COM port just by connecting. So yeah, that's what I'm using right now.
And so there's no operating system or anything, right? So is there some other electrical part of this or whatever that converts your UI and everything to signals or?
So there's firmware that's running on these are good questions. It's showing me parts of the presentation that need to be fleshed out beforehand. So along with this host UI, there's a companion firmware that's running on the device. And so there's in a few slides, I'll get a little bit more into this, but like the host UI and the base of the firmware that's running, they have a contract as to what functionality they're going to provide to allow additional custom functionality to appear. So like, for instance, one of these commands is get registered commands. So I can click this and that spits everything out. And just the host UI knows when it connects, it's going to call that. But other commands like, let's see here. Here's one where we just show highlights on the screen. That's a custom firmware command that's in the firmware, and it's registered to execute. And the host UI just knows when it sees certain tokens, it's gonna splash the screen like that.
And what we're seeing here is this.
I probably
link?
should have shown this. Are you guys able to see me? I can't see. I can't. I'm not watching the video.
Yeah, we can see it.
Okay, so I have this device connected right now. This is something I put together. So there's a microcontroller here, and then so when I hit connect, I actually established a connection with a device like this. And
is it an Arduino?
It is.
Okay.
Yeah, this is a knockoff Arduino Nano.
And what language is this? Like your own language, or is this?
This is C. This C and C++.
So I'm sorry, real quick. So you're using the base load, the base loader for the Arduino through the Arduino IDE, or are you just going separate, complete load difference?
So I use the Arduino IDE to come up with a I call it the base kernel of the EDPF. That's a base firmware load.
Okay.
And then it has some classes in there that allow you to register what additional commands are available. So like what additional things will show up
Very cool. Okay.
in this UI. And then so like the base load says I need to be able to get the device info. I need to be able to get the registered commands. And then from there, everything can layer on top of that. In addition, there's like the I/O, the handshaking of sending data, knowing when it's safe for the computer to retrieve data, and all of that's kind of baked into the EDPF firmware. But then you can start layering on your own commands. So for instance, I'll just jump right into here. I did the Preem IO one, but the EDPF kit read, that's something that comes out of the box, and that's a companion for this. I made this device as a approachable sensor set. I wanted something real world to kind of show off, like here's the firmware and the host application software that you can use. And so like, what's something real world that everyone will just kind of grasp? I was like, a controller that, that's about as real world as it gets. And so calling that command that I have specified in there, I can start doing readings on the board. And so right now I'm doing the joystick left and right, and you can see that first number is kind of jumping from like the high to low. And then if I do up and down, that second number is changing. Now I'm going to press in the digital on the joystick, and then now I'm pushing a few buttons and pulling them off.
Another quick question. So your interface for the joystick is through the GPIOs, or are you going the USB port?
The Arduino is using the GPIOs to connect.
Okay,
Sorry,
and then
I should just show this here. So
yeah, right.
So there's data buses here. So I can't really. Well,
oh, I'm sorry. So is it serial or UART just handshake, or are you just going GPIO by GPIO?
It is going GPIO from the sensor here to the Arduino. Then the Arduino is running C and C++ code, and then going RS-232 over the USB to this to the host application.
All right, and I just expanded all my knowledge. I have nothing left. That was it. That was the top end. So
hey, I hope you have more questions. So please throw them at me. That's awesome. Thank you. Okay, and so so one of the commands that comes out of the box as part of, you know, like, hey, get to know this technology and see if it can help for you, is the EDPF kit read command. As I said, I made the controllers as a approachable way to show off what I have available in the software and firmware. And so I already showed that, like, you know, we click the buttons and we manipulate our sensors, and then we get some different readings. Well, another one of the tools I added in was a macro tool. And so the macro tool allows you to do the same, you know, same set of instructions. You can set it on loop, or you can just, you know, do it as a one shot. And so I'm going to do this twice. So it's going to be, and let me change the sleep so it's not so long. So I'll do 500 milliseconds in between each. All right, and then so I'll hit the loop button here, and I'll start manipulating the controller. And so I'm sitting here pressing buttons and stuff, and you can see that stream of data is coming through. And so just keep that in mind, because like a lot of these controls kind of tie together. The last control I'm going to go over is the charting control. So the charting control allows you to, I got to go in my notes here. All right, so the charting control uses a simple expression syntax to describe the data coming from the device. And the host UI uses the expression to parse device output, and it plots X number of data values onto Y number of data charts. So for the EDPF kit read command, we can use an expression string like this. So the expression string starts with the same prefix of what was being output by the EDPF kit read command. So if I hop back, you can see that, you know, kit : is the first start. This wasn't meant to be a pun on you, Kit. I just realized that was.
It's awesome. I like
yeah.
it.
Okay. I'll get past that. We'll go on. So after that prefix comes a set of comma separated tuples. In each tuple, there's the data variable name and the chart. And you can specify which data value goes on which chart just by having common names. So you can see here that all four of those push button are going to be put together. And so I'll start manipulating. Right now I'm doing the joysticks, the X and Y. I'm pressing in on the joystick pad. I'm pressing 1 button, and then 2 button, and 3 buttons, and 4 buttons. And then we can change our settings. So here's where we can change where that is programmed. And I'll go ahead and just drop the digital pad onto the push buttons, just to show that it's not that big of a deal to make a change.
And all your input, so quick question, all your chart data is digital versus, you're not doing any analog charting, right?
It depends on like, it's whatever your data is coming out as. Okay. So like this charting tool that I'm using, there's surprisingly very little code to do this charting. It knows how to expand and shrink the graph based on the data that it's getting.
Okay.
So cool. Like it handles, yeah, if you had you know, some values in between 0 and 1, like it would handle that without that big of a deal.
All right, cool, thanks.
And you can see it kind of shifted. I don't know if you caught that, but it shifted as all of a sudden a bigger number came in. It realizes that it needed to expand.
Okay, yep, got it.
And then lastly, we can save the data off. if you want to analyze it later. All right. So that's it for the EDPF host UI. The host UI established a connection with the device. It configured UI elements to match the functionality of the firmware. The functionality of firmware is wrapped in commands, which have optional parameters. And we added some command calls to the macro tool, set the macro tool to loop, repeating the commands. And last, we use a charting tool to plot the data coming from the EDPF demo kit. So now let's take a quick peek at the firmware that works in conjunction with the host UI. The device needs to be able to describe its functionality, and the firmware does this through a registration process. Users of the EDPF firmware will write code to register commands and optional parameters to those commands. So think of the EDPF commands and parameters much like software functions and function arguments. And the host UI knows how to interrogate the firmware of those commands and provide a custom UI element for each command that it finds. So in addition to firmware command, in addition, the firmware commands have callback methods assigned to them that trigger when the host application sends the command name to the device. So here's a simple example where a callback method is registered with a name. The one associated parameter is assigned to this as an unsigned 8-bit integer. And so with this bit of code, the firmware knows how to describe itself to the host application. The host application will create a UI element and a named input field that is strongly typed. And the host UI software does this with out-of-the-box functionality. So no UI development is needed to execute that callback method and pass in data. And here's an example callback method. So when the firmware detects the param.io command token, it executes the command's callback method. Inside the callback method, the firmware retrieves the parameter by name, and it can make further use of the data with whatever custom firmware the developer coded. And that's really it for the EDPF. The main focus is on reducing the code needed to interact with embedded device and offering a tool set to speed up development. And so I'm using the project to cut down on my own development time and hoping it'll provide some benefit to others. Since my project is geared towards prototypes and prototypes are by nature geared towards innovation, it's almost as if my project has the goal of innovation with the idea of speeding up more innovation.
What kind of stuff are you prototyping?
So I've been working on like 360 visual spin systems. I've also worked on a medical device to analyze the gas mixture. Yeah, so but what I found is as fun as those projects were, and it was why I started developing back again in electronics, I kept coming back to the framework over and over again. And so with this being like the public rollout, I only feel like only now and going forward will actually be doing a whole lot of real world projects as opposed to keep pouring more and more functionality back into the framework.
Yeah, I really like it. That's awesome. Quick question for you. So
yeah.
So like again, I'm the novice here. So so I play around with like Raspberry Pi, and then like Adafruit is where I'm getting a lot of my devices, and they have their preset, libraries. So in something like this, your goal is to just to understand. So like if I'm like, let's say I'm going to do the a gas sensor, SPS 330 or something from. Yeah, I guess that's not Adafruit, but it's so basically it has a set of protocols that are already in place for how the data is interpreted, and I think it uses IC2 with something like this.
I2C.
Yes, yeah.
Yeah.
So
okay.
How would you see this working? So let's say I'm using a Raspberry Pi. How would you envision that interfacing with that device?
Yeah. Is it the Pi Pico, the really small
No,
form
well,
factor ones?
no, actually, if I'm using the, well, let's back up. Let's say, not saying
Okay.
that one. Let's just say like a DH22 or something with a Raspberry Pico. So again,
Okay.
that's not I2C or IC2, right? So how would you envision that working with that device? Just a simple sensor.
Sure. Yeah. So where I think the EDPF has its most use cases is where you have like low visibility into what's going on with the device, and so it would facilitate, say, setting up your I2C connection to your sensor and then being able to read those back. So you won't have to write the custom code that will allow you from your computer to see what your sensor is seeing. And so, you can imagine like when you're setting up your firmware to say like, I think I need to enable these bits
Right.
to set up this data bus and start getting data back. That's where it shines. It's almost like the Arduino IDE itself does have a console tool and a graphing tool, but
Yep.
this kind of in my opinion, this kind of takes it a step further, where it's like not only does it have those capabilities, but you have the ability to have UIs that provide additional fields. So imagine you weren't sure if you wired up your I2C sensor, and a lot of times it can a lot of times you need to like change one or two pins, and that will
Right.
change the address of the board, and that could be something you could program in as an input value to say like, I'm going to dynamically change this and keep testing my sensor, keep reading my sensor until I actually see a stream of real data, as opposed to like either the firmware will lock up because the device is not responding, or you'll just see something that's like flatlined, all zeros or all Fs, or
Yep.
garbage. So
Yeah, that's a great example, because that's definitely one that the IDE absolutely fails on. So okay.
yeah, it's kind of like you might throw something in your code, and then like that's like throwaway code at that point, where I took the idea of like I want to be able to have these discrete methods I can call, and they're not really going to interfere with each other, because I can just execute one at a time. Where if you're working with the Arduino IDE, it does have a console tool, but like you would have to write the code that would do the handshaking on like, okay, I'm typing in text and I hit enter. Okay, now how do I route that instructions that you typed in to the correct function? How do I parse those input values? So it's really just like get rid of a lot of the boilerplate. And I don't know if this will be like what gets fielded in production scenarios. I think it's more of like it was definitely more of like the UI component of Swagger to myself. It's like most people don't use the UI component of Swagger in production. It's more of like a troubleshooting tool. But there's a lot of time saved if you can understand what's going on or what's going wrong in a certain scenario.
Mm-hmm. Sure. Yeah, that's great. I like it.
Thank you.
So it's more a developer tool, like used kind of early on. It helps you kind of get going, understand your inputs, get started quickly, that sort of thing.
Yeah. I don't think it'll be the UI for the end user. I mean, it's open source. Like if anyone wanted to just push that on people, like I would be glad to have as many people using it as possible. But it's definitely shows you the nuts and bolts of what's registered to operate for that firmware. So yeah, it's definitely like a developer speed up prototyping tool. Cool. Well, thanks for all the questions. Anything else for I jump on?
Yeah, I have one that's sort of tangential, but what is ECS?
I'm sorry?
What is ECS or CES or SEC or that logo there on the?
Oh, shoot. Sorry. I'll get into that. So I'm starting a business. I don't know. That should not have caught me off as guard as it. It should not caught me as much off guard as it did. I'm starting a business, and like my idea was to put out into the world this open source project as kind of get to know me and, kind of show off what I do. And I don't know if the business will take off or the open source project will take off. Both, neither. We'll find out. So yeah, that's where this is headed into. I'll have a shameless plug at the end. All right, so let's do a quick compare and contrast of embedded development versus more common workstation-oriented development. And in the end, I'll go over how to get started with electronics development on your own and some closing information. So a big difference, debugging firmware tends to be harder than debugging software. So some hardware platforms require the use of special hardware dongles to enable debugging, and this is usually on the higher end platforms. For lower end platforms, you may end up dedicating debugging through the only serial I/O port, and thus you have to sacrifice this very important I/O channel, which you may need for your system operation. This often leads to the poor man debugger, which is printf, as the only option, which is not great. Sometimes it's all you have. So as you imagine, printf debugging is ideal. You have a pretty low visibility into what's going on, and it takes a comparatively long time to add print statements, re-download the code, and get to the code in question. So you can drive, this can drive development cycle time way up, really slows down iteration frequency, and makes development time drastically increase. So avoid the printf zone if you can, but sometimes you can't. Some other pro tips, create firmware isolation loads. Often when a piece of hardware is malfunctioning, it locks up the execution of your firmware and your device is bricked, as in it's as useful as a brick. So when your device becomes sufficiently complex, make firmware loads that perform self-test on different ancillary hardware components of your device. So think of these firmware loads like unit test, and that they isolate discrete functionality as much as possible and allow you to hone in on the problem. Another tip, focus on small changes. With less visibility into what's going on with the code, keeping your deltas for each iteration minimized is best. That's really a good programming practice in general, but I would say even more so for hardware development. As far as similarities, appropriate use of data types is something that benefits you really well in embedded development. Just like other forms of development, some things might seem inconsequential on workstations, like, say, saving ints to floats or overusing strings, and that can have really big performance impacts, like gobbling up precious memory resources and causing needless delays that are a lot more painful on embedded devices. So some platforms won't have great floating point data support, and the order of operations on floats over ints can be orders of magnitude longer. Also, many data type principles of workstations are database programming applied to embedded programming. For example, use the smallest data type possible to fit your data is usually the best approach. So one big difference is firmware programming can be quite different than most software programming, in that most often with software programming, you usually reach for whatever libraries you have available to cut down on the amount of code. Pulling in common software dependencies in firmware can have huge memory ramifications. And something as simple as pulling in data types like strings from a standard library or using a dynamic memory allocation, that can rapidly consume your constrained resources. So instead of dynamic memory allocations and strings, you often use raw character arrays and fixed size memory buffers. I remember this hit home once when I was I had to look up how to do a round operation with only integers, and I was just going from normal like workstation programming to realizing I had to do that was kind of where it was like, aha, like things aren't the same anymore. Another similarity is that versioning is key. So just like with software clients that access APIs and the compatibility aspects that apply, the general principle applies to host machine software that interfaces with firmware. And I would go one step further and say knowing what firmware is running on your device is easy to mess up if you're not diligent. So creating a mechanism to know that you're running the absolute latest is key. hardware can malfunction in funny ways. Like the firmware download can silently fail, or your storage device no longer accepts writes. That, or you just get in a habit of simply resetting the device without actually downloading the firmware updates you just coded. And if you make that a mistake enough times, you'll create mechanisms to know that your firmware changes are indeed executing on the device. And for this reason, the EDPF reports the firmware version on command. And my mantra is, when in doubt, bump the version number, re-download the firmware, and check the echoed back version number. So I've gotten in the habit of doing that change. Basically, I'll always change the firmware version on every single change I make. Whether or not I check it, that's usually the second order step. Is okay, it's not behaving how I thought. Let me just verify that it is indeed executing what I think it is. Another difference that you'll find, embedded devices and that your language and tooling options are likely to be pretty constrained. So C and C++ dominate, and a much smaller number of platforms support slimmed down versions of Python. Jacques, if you're still around, what are you using?
For devices? I'm actually going all over the place. So if I'm using, for example, I was using any kind of Arduino, obviously the C++, and then MicroPython for the same devices. So for ESP32, I use the C++ and I go through VS Code, VS Code, and I use the platform IO. But one of the things as you're talking, I was wondering, like you talked about the firmware and everything like that. The problem with, like, for example, the ESP32, it seems to be a lot of overhead. Again, with space limited for memory, there's a lot of overhead even before you put your basic code in there. Can the process you're talking about kind of slim that down?
No, it does the opposite.
Okay.
It takes the path of I will be the easiest to interact with. So just without adding anything into the Arduino Nano, and as in just starting off with the base kernel of the EDPF, it's already used like 50% of the available memory. So definitely, this should actually be a slide. That's a great point. When you're prototyping, buy the bigger board than what you need, because it's usually not a whole lot extra money. And then if you're going to do large runs, then you can always, pull it back to like the most economical thing.
Well, one other thing I think when you're bringing up about the hardware and the firmware, especially if you're buying the cheap boards like ESP32s, there's a lot of different manufacturers. So like, for example, Raspberry Pi or Raspberry company is standardized. But if you get out into other small end boards like the ESP32s, your pin configurations can be different. Your code, access can be different. So what you're talking about, being able to actually have a better insight to the actual responses from the board would be helpful.
Yeah. So the only things I had to add were you often only have one or two practical choices for languages, and tooling will probably be you'll be up to the mercy of what the vendor provides, and maybe one or two other options by something that's open source.
Gotcha.
Hey, just crazy question.
Yeah.
Does this type of language have any kind of mechanism like they do in JavaScript, where they do tree shaking and pull out every path that's not invoked there?
So the EDPF, as it's written now, there's only the C/C++ implementation. I don't see any reason why there couldn't be a MicroPython implementation, other than just I haven't written it yet. I think C and the C++ compilers do a pretty decent job of, if it can realize that it's orphaned code, of not using up the code space. I think those are kind of baked in to a lot of them. Is that what you're talking about with tree shaking?
Yeah, so it's optimized out altogether if it's not used.
C and C++ are pretty lean and mean as far as it goes, and because of that, sometimes it can be harder to code against, just because the compiler doesn't, the tooling in the compiler doesn't do as good of a job of holding your hand and pointing out errors. It'll be more like it just doesn't compile, and you get really cryptic error messages as to what's going wrong.
So if you're using the Arduino or like VS Code, the platform IO, the system you're working with compiles in that compiling, that when it's compiled, it grabs your as a module per se, or?
I see. I use two IDEs. I use the Arduino IDE. For one, I want this project to always be accessible to the majority of people, and I think the majority of people using Arduino boards are going to use Arduino IDEs, the Arduino IDE, and then I also use Visual Studio with a $30 plugin because it has better project management. But it compiles in both, and even after I do development in that Visual Studio environment, I still compile it with Arduino and make sure that it's still working. Because if I've done anything that in that Visual Studio environment that I can't do on Arduino, then I've kind of violated what is going to be like a core functionality of what I want this project to be. Matt Johnson, are you still in the audience?
Yep, I'm here.
You've done just a cursory test with like the ESP, right?
Yeah, I did. And
What IDE were you using to develop against?
I think I was using just Arduino. I didn't use anything special.
Okay. Oh, you were doing the Arduino IDE and then using the ESP device. Okay. I didn't know if you needed a different IDE when you were doing that programming.
No.
Okay. Cool. Thanks for the questions. How are we doing on time, Kit? Do we need to speed things up? I can skip this slide. I think I got
Oh, you're good.
a handful. Okay.
You can go until 7 if you want, but
okay. I don't think I'll burn too far past that if we do get that far. Who here is familiar with Endianness or structure member alignment?
Me.
Yep.
I'm sorry. Can you explain either of those?
Well, so I think I can explain both of them.
All right.
So can you hear me?
Yes, sir.
So for Endianness, different operating systems lay out the 32-bit integer, or I don't know, it's probably 64 also. They lay them out in different orders. So the first 16 bits will be on the left or the right, depending on what it is. And it used to be like all the Unix platforms and everything laid it out in large Endian, I think it's called, little, and Windows and Microsoft did little Endian, and over the internet the standard is big Endian. So you always had to worry about if your data was what kind of machine it was coming from, right? Mm-hmm. So, and we had this problem where we had a bunch of sensors everywhere that were Solaris. And we brought all the data back, and the government wanted me to put it on a Windows machine, and I'm like, that's going to be a problem, right? So there are tools to flip those bits around in the order that you want them if you know that they're coming in the wrong order or whatever. And then on the other side, data alignment, operating systems can lose a lot of time because if they don't pack in the data in the right order. So people used to like manually calculate all this out, right, and put their struct members in a certain order so that you would end up having like, okay, so your red and green thing over there, you wouldn't have all this padded out space, right? So you would flip like the Y up under the X, so it would be the minimum amount of data transferred back and forth between memory, minimum amount of calls. And so some systems can optimize that in now. And people still, I think, manually look at it.
Yeah, thanks for that. Yeah, that's great perspective. The place I ran into it was a host machine that you could just think of a workstation interacting with a USB device or a PCIe device, and you're sending those data structures back and forth, and you got them defined on both sides of the firmware and the software, but then yeah, the data ordering could be completely backwards, and the member alignment could be completely off. So then you have to find certain keywords that will ultimately control the packing, or completely flip every member as it's coming across. And so that's another fun one to just be prepared to understand the impacts of bus width and endian type of your microprocessor.
So dumb question, but I'm thinking of the like big data use case where maybe you're like, as a data engineer, I might be on the receiving end of hundreds or thousands of these devices. Is the big endian and little endian thing not taken care of by the boards? It's like, so if I'm consuming it in the
So
cloud,
some microprocessors will prefer big endian, and then I'm sorry, whoever spoke first about saying like when they switched to Windows that it was little endian. So like when you have that handshake in between your big endian microprocessor and your Windows machine or your whatever machine that's little endian, you'll have to have some code somewhere that does the flip. So as the data is going both in and out, you'll have to make sure and flip it all. I can't say that I know the preferred way to handle it. Just besides the fact that I know I've needed to handle it with every device that's not little endian, because I've typically interacted with little endian workstations.
okay, thanks.
Hey, can I make since we're big data thing here, not making any assumptions, but this is a good time, I think, to just mention that one of the reasons people like column their data is because of this specific thing, right? This mixed data can cause massive cache losses or cache non-hits or whatever, right? So when you're reading like a standard data type from a column, it's all going to be in order. So these processors that do prefetch and everything have a far better chance of having a cache hit off the prefetch than some struct like this. There's like 17 different types of data. So the very next one is going to be wrong, and it's going to have to have a hit, a miss, and then go fetch again, right? Does that make sense?
Okay.
So would you are there like columnar data stores that you would use on a microprocessor, or?
So sorry, I don't have any idea. I just meant this theory right here is one of the same reasons that they use columnar data stores.
You have to worry about the packing, because
Oh,
it's packed columnar, and then you can just do simple arithmetic, simple pointer arithmetic to jump in between your spots. I've definitely worked in systems where the microprocessor is kind of like the low-powered brain, and then it's attached to one or more FPGAs that can do like massive amounts of data transformations in parallel. Like a video, I did something that was essentially a video card for high capture video transformation and compression. And that was that setup where like there was a ton of data flowing through the FPGA, and the microcontroller kind of coordinated it all. And if the end user wanted to make some changes to the device operation, it would first pass information from the computer to the microprocessor, and the microprocessor would fan out those instructions to the FPGA. Then it could do things like, say you had a giant blob of data and just transform it. All right, so how to get started at home. So don't let any of the differences with the embedded device programming dismay you. The materials, the tooling, and devices, they've only continued to get better and more approachable. And in addition, I put together a quick cheat sheet to supplies and software you can use to get started at home. So for embedded device IDEs, you really pick your hardware and know that your IDE, that you'll probably have just a few options based on that. So the Arduino IDE, that's free. That's for C and C++ languages. MicroPython, I think that's used on ESP devices and a couple other devices. I prefer the Visual Studio Community Edition, which is free, but then I buy a $30 plugin, and then I do C and C++ programming for Arduino boards. But I think if you chose any of those, and there's probably some that I'm leaving out. I think Jacques said Python. There was like a
VS
Code. VS Code.
Yeah, and VS Code has a Platform IO add-in.
Okay, that one's been that's your go-to.
Well, yeah, it's all it is actually it's just compiling the Arduino IDE code or IDE. So
okay,
yeah,
cool. The visual micro extension does have a debugger built into it, but you completely take up the USB port. So if anything you're doing, including the EDPF, if anything you're doing would require a serial I/O, you're kind of like out of luck there. But there are definitely devices that have multiple serial I/O ports, because sometimes you'll have one master microcontroller talking to multiple daughter cards with their own microcontrollers. So it's not to say that you're completely out of luck, but other times there's other IDs when you start getting into more expensive boards, but this is definitely the bread and butter for home starters. You'll want a digital multimeter, so that's for taking measurements. You can usually spend about $60 or less on that. You'll want a soldering station. I've learned the hard way, don't cheap out. Plan on spending about $100 or more. I tried to do a $50 one, and I just ended up throwing it away with how frustrating it was. There's a tool called Helping Hands. Would you imagine that there's these metal clasps that stick up, and you can like put whatever you're working on and soldering in these metal clasps, and they'll have magnifying glass that you can put right above it. You'll want an ESD mat so you don't accidentally shock your devices and mess them up. I've also been told you don't want hot balls of melted metal in your eyes, so safety glasses are definitely called for. I haven't tested that one out myself, so I wear the safety glasses, and good lighting. So with just a few $100s, you can get yourself a pretty nice setup.
Can I ask a question?
Absolutely.
Have you tried any cheap, or do you have any recommendations around spectrum analyzers? I know there's like these little weird cheapy looking ones for like 50 or 60 bucks.
For like measuring waveforms and stuff?
Yeah.
No, I haven't. I've always been more the digital guy. And I know that's there's a huge field that you need to know the analog side of things, measuring
They'll track
waveforms in the air
stuff too.
Yeah. So like a lot of times you can have it like capture, your waveform on a pulse or whatever.
Yeah.
No, I haven't. Most of the time I've used them, it's been I've been in a high-end setting where like that was just, they had multiple of them laying around. I don't have any I've at my house, but I know people that do, that are also hobbyists like me, and they do. They're kind of more on the analog spectrum. They know a lot more of what they're doing in that area than I do, I should say.
Cool. Thanks.
Yeah. So if you're looking for even lower startup costs and live towards St. Louis area, there's a few Makerspace groups I want to point out, and they have all that equipment that I just called out, plus a ton of additional tools. They have a really awesome member base with diverse interests and hobbies, and there's at least 2 in the St. Louis and St. Charles County area, and they provide 24-hour access to everything you need to get going. So there's Arch Reactor in St. Louis, and then Inventor Forge in St. Peters. And there, They have 3D printers, lasers, electronic stations. They have ton of woodworking, ton of metalworking stuff. Really, and I'm leaving out a lot of tools here, but it's a lot of people are there to they like create games and toys. They run their businesses out of there. There's people that like run like fly fishing. I know someone who's prototyping some medical device there. And lots of entrepreneurial type spirits there. Fix stuff around the house or just have a hobby to feed their passion. They also do community-based activities like promoting STEM to local youth. They have social activities for their members, and they visit conferences together. And I highly recommend checking out either of those groups. Great people. The benefits of the membership, which are typically like $40 to $60 for individual to a whole family, I think it's well worth the cost. All right, now for the shameless plug. So in addition to my day job, I'm a hybrid of a software engineer, a data engineer, and a manager. I've also started my own company, and it began with the idea of making development easier for electronic devices. My company is Electronic Computing Solutions, and its mission is to empower you to be more effective in your technical endeavors. In addition to providing software and firmware for end users, I've also had the fortune to provide technology solutions for engineers, boosting their productivity and helping them complete their work faster. And that's where my company focuses its software development efforts, helping others be more productive. And to give you some insight as to how I operate as an engineer, I've been asked by others that see me work, are you pumping your fist in the air in celebration? And my answer is yes. I just automated this awful manual process we've been suffering through. And so when that new functionality works for me for the first time and I get to provide a boost to others, that's what gives me my engineering dopamine hit. So if you know someone that's looking for help with their electronics and software project, please have them reach out to me and we'll talk. I'm most easily reached on LinkedIn. Also, if you think the EDPF project can help you or your company, I'd be happy to share all that I can on that front and see what use cases that can facilitate. All right, almost done. So I'm doing a giveaway for anyone that's interested in electronics. I have a mailing list for upcoming Basics of Electronics course, which will be taught in the St. Peter's Makerspace around April. Anyone who signs up for the mailing list will be entered into a drawing where I'll give away 6 of these EDPF demo kits. And up to 3 will be given to tonight's attendees, assuming I get 3 signups. So please sign up if you're interested with the link at the bottom left. That's electroniccomputing.com/contact. And please put demo kit big data in the comments so I know you attended tonight. And I'm going to draw the names on February 8th. Here's the bunch of links I have for stuff I kind of went over tonight. And if anyone wants to see the slides, I have them available on my site at that URL there. That's all I had. Is there any additional questions I can answer? I'll paste this link in the chat.
Great presentation. Thank you.
Yeah, that's awesome.
Thank you.